Look up at the night sky, past the glittering stars and swirling galaxies, and you'll find something far more unsettling: vast patches of darkness so dense they blot out the light behind them. These are dark nebulae, cosmic clouds of dust and gas so thick they swallow entire stars, hiding secrets we've only begun to unravel. Imagine standing at the edge of one, staring into an abyss where the laws of physics seem to twist, where light itself vanishes without a trace. It's not just emptiness, it's a curtain pulled across the universe's stage, concealing mysteries that defy our understanding. What lurks inside these shadowy realms? Some dark nebulae cradle newborn stars, their faint glow smothered by the very material that birthed them. Others stretch like ghostly fingers across the cosmos, their shapes so haunting they've earned names like the Horsehead Nebula or the Coalsack, a void so vast it's visible to the naked eye from the southern hemisphere, a black hole in the sky that isn't a hole at all. And then there are the ones that shouldn't exist, defying our models of how dust and gas behave, leaving astronomers scratching their heads. These aren't just absences of light, they're active, dynamic puzzles, challenging everything we think we know about the universe. Today, we're diving into 25 of the most enigmatic dark nebulae, each one a story waiting to be told. From the eerie Barnard 68, a perfect sphere of darkness that appears to float in space like a cosmic bubble, to the tangled veins of the Snake Nebula, where magnetic fields twist dust into impossible shapes, we'll explore the questions they raise and the breakthroughs they've inspired. Some hide rogue planets drifting alone in the cold. Others may be the birthplaces of future solar systems, their secrets locked away until technology catches up to our curiosity. This isn't just a tour of the universe's shadows, it's a journey to the edge of what we can see and what we're still desperate to discover. Barnard 68 isn't just another dark smudge in the cosmos, it's a cosmic enigma wrapped in near-perfect darkness. Nestled within the constellation Ophiuchus, this dense molecular cloud floats like a shadowy sphere against a backdrop of stars, so pitch black that not a single photon escapes its grasp. What makes it extraordinary isn't just its darkness, but its shape. Unlike the chaotic, sprawling tendrils of most nebulae, Barnard 68 is almost perfectly round, as if some unseen hand sculpted it with celestial precision. Astronomers have spent decades puzzling over how such a symmetrical structure could form naturally in the turbulent swirl of interstellar space. Inside its opaque depths, temperatures plunge to just a few degrees above absolute zero, cold enough to freeze atoms in place. Yet despite its frozen stillness, Barnard 68 is anything but inert. Deep within, gravity is quietly at work, compressing gas and dust into knots so dense they'll one day ignite as newborn stars. It's like a cosmic cocoon, dark and silent now, but hiding the potential for stellar life within. This makes it a goldmine for researchers studying star formation, offering a rare peek into the earliest, most secretive stages of a star's birth. But here's the twist: Barnard 68 shouldn't be this stable. Molecular clouds this dense usually fracture under internal pressures or spiral into irregular shapes, yet this one defies expectations, holding its form with unnatural persistence. Some theories suggest magnetic fields act as invisible scaffolding, while others propose turbulent gases somehow balance themselves into this eerie symmetry. Either way, it challenges our understanding of how cosmic structures evolve, proving that even the darkest corners of space still have lessons to teach. And because it's relatively close, just 500 light-years away, it's one of the few dark nebulae we can study in intimate detail, a shadowy laboratory at our cosmic doorstep. From a distance, Barnard 68 looks like a perfect hole punched through the fabric of the night, a circle of nothingness where stars should be. This hole in the sky illusion isn't just a trick of perspective, it's the result of an almost unbelievable density. The cloud's dust grains are so tightly packed that they absorb and scatter visible light, making it completely opaque. To the naked eye, or even through most telescopes, it's as if someone turned off the stars in this one patch of space. But switch to infrared and the story changes entirely. Infrared light, with its longer wavelengths, slips through the nebula's defenses like a ghost. Recent observations from telescopes like the Very Large Telescope and the Spitzer Space Telescope have peeled back the darkness, revealing a hidden nursery of protostars deep inside. These infant stars, still swaddled in thick cocoons of gas, glow faintly in infrared, their heat signatures betraying their presence. It's as if we've been handed night vision goggles to spy on the universe's best-kept secrets. What's even more fascinating is how these protostars warp their surroundings. Their gravitational pull sculpts the nebula's interior, creating intricate filaments and knots of dust that no model predicted. Some of these structures look like cosmic umbilical cords feeding material to the growing stars. Others twist into spirals, hinting at magnetic fields weaving through the chaos. Every new observation adds another layer to the mystery, proving that Barnard 68 isn't just a dark spot. It's a dynamic, evolving system, bustling with activity we're only beginning to decode. And then there's the timing. Astronomers estimate this nebula will likely collapse entirely within the next 100,000 years, a blink in cosmic terms, giving birth to a small cluster of stars. We're catching it in a fleeting moment, like stumbling upon a chrysalis just before the butterfly emerges. That rarity makes it a priceless laboratory for understanding how stars like our own sun first ignited. Yet, even as we study it, Barnard 68 taunts us with unanswered questions. Why does it retain its perfect shape when similar clouds fracture? What unseen forces keep it stable? The more we learn, the clearer it becomes. This dark nebula is a masterclass in cosmic subtlety, hiding its most profound lessons just out of sight. Hanging like a smudge of cosmic soot against the Milky Way's brilliance, the Coalsack Nebula is impossible to ignore. For centuries, this sprawling dark cloud has dominated the Southern Cross, its inky silhouette cutting through the starry backdrop with such stark contrast that it's visible to the naked eye, a rarity among dark nebulae. Indigenous cultures across the Southern Hemisphere wove it into their celestial lore long before telescopes existed. The Aboriginal peoples of Australia saw it as the head of the emu in the sky, a celestial ancestor whose dark form stretched across the Milky Way. To the Inca, it was a portal to the spirit world, a void where earthly and cosmic realms intertwined. This isn't just a cloud of dust, it's a cultural touchstone, etched into humanity's collective imagination. Yet for all its prominence, the Coalsack defies expectation. Most nebulae of its size and density are bustling stellar nurseries, their gas collapsing into newborn stars. But the Coalsack lies eerily quiet. Despite containing enough material to form thousands of suns, it shows almost no signs of star formation, a cosmic paradox that has left astronomers baffled. Theories abound. Perhaps its internal turbulence prevents gas from condensing, or maybe magnetic fields lock the particles in place like an invisible straitjacket. Some suggest it's simply too cold, with temperatures hovering near absolute zero, snuffing out the spark of stellar birth before it can ignite. What makes this stillness even stranger is the nebula's proximity. At just 600 light-years away, it's one of the closest dark nebulae to Earth, offering a front-row seat to study its mysteries. Modern telescopes have peeled back layers of its darkness, revealing intricate filaments of dust woven through its core, structures so delicate they resemble cosmic lace. These filaments hint at subtle gravitational whispers, the faintest stirrings of activity beneath the surface. But why hasn't that activity sparked star formation? The Coalsack seems to exist in a state of suspended animation, teetering on the edge of transformation but never quite tipping over. The answer might lie in its environment. The nebula floats near the edge of the local bubble, a vast region of sparse, hot gas carved out by ancient supernova. Some researchers speculate that external pressure from this bubble could be compressing the coalsack just enough to stabilize it, like a hand gently cupping a mound of sand. Others point to its unusual chemistry. Traces of complex molecules frozen onto dust grains might be acting as cosmic antifreeze, slowing down the collapse. Whatever the reason, the coalsack stands as a reminder that even the most familiar celestial objects can harbor profound secrets. It's not just a shadow in the sky, it's a challenge to our understanding of how stars are born and why sometimes, against all odds, they're not. Hidden within the coalsack's vast darkness lie smaller, denser mysteries, tiny pockets of shadow known as dark globules. These isolated knots of gas and dust, some no wider than our solar system, drift like black marbles suspended in the void. Unlike the nebula around them, these globules are so compact they could fit between stars unnoticed, yet their potential is astronomical. Theory suggests they should be stellar cradles, their dense cores collapsing under gravity to ignite new suns. But when astronomers peer into their depths, they find only silence. Not a flicker of heat, not a whisper of light, just perfect stillness, as if time itself has paused inside them. What makes these globules so baffling is their defiance of cosmic logic. In similar environments across the galaxy, clouds this dense are already birthing stars, their interiors swirling with chaotic energy. But here, the rules seem rewritten. Some researchers propose that the globules are simply too young, their internal pressures still building toward a tipping point we haven't caught yet. Others point to their unusual chemistry. Spectrographs reveal molecules like carbon monoxide frozen onto dust grains, creating a kind of interstellar gel that resists collapse. It's as if the universe hit pause on star formation, leaving these globules hovering in a state of eerie potential. Their isolation adds another layer of intrigue. Most star-forming regions are chaotic, with neighboring stars or supernovas stirring the pot. But the coalsack's globules float undisturbed, shielded from outside interference. This pristine environment makes them cosmic time capsules, perfect laboratories to study how stars begin when left entirely to their own devices. Yet their stillness raises a provocative question. What if star birth isn't just about density and gravity? What if it requires some external trigger, a nudge we don't yet understand? The most tantalizing clue lies in their shapes. Some globules are teardrops stretched by invisible tides, others are near-perfect spheres, as if sculpted by an unseen hand. A few even sport comet-like tails, suggesting they're drifting through subtle magnetic fields. These odd forms hint at hidden forces at work, forces that might be the key to their dormancy. If we could unravel why these pockets refuse to ignite, we might finally understand what truly sparks a star to life. For now, they remain cosmic riddles, dark and silent, holding their secrets tight. Slithering through the constellation Ophiuchus, the Snake Nebula earns its name with uncanny accuracy, a sinuous ribbon of darkness writhing across the starfield like a cosmic serpent frozen mid-strike. Unlike the chaotic blobs of most dark nebulae, this one stretches over 30 light-years in a nearly unbroken curve, its filaments so precisely aligned they seem sculpted by some celestial hand. But the real marvel isn't just its shape, it's the invisible force behind it. Magnetic fields stronger than anywhere else in the region grip the nebula's dust like puppet strings, twisting it into these eerie, elongated forms. Normally, gravity alone dictates how nebulae collapse and clump, yet here, magnetism overpowers even gravity's pull, weaving the dust into filaments thinner than a solar system but stretching farther than the distance between stars. Peering into the snake's depths reveals a labyrinth of subfilaments, threads so fine they resemble cracks in shattered glass. Each one traces the path of a magnetic field line, a roadmap of forces ordinarily invisible to our telescopes. Astronomers call this B-field alignment, where dust grains act like microscopic compass needles, all pointing along these hidden lines of force. It's as if the universe sketched the nebula's blueprint with magnetism, then dust obediently filled in the lines. This level of order is unheard of in most nebulae, where turbulence usually scrambles such precision. The snake's filaments shouldn't exist this way, not unless something extraordinary locked them in place. That something might be the nebula's location. It coils through a region dense with young, massive stars, their fierce radiation and stellar winds battering surrounding clouds. Normally, this would shred a nebula to pieces, yet the snake thrives. Researchers suspect the magnetic fields act as a shield, channeling the chaos into orderly strands instead of letting it dissipate. Imagine blowing smoke through a comb. The teeth arrange the smoke into parallel streams. Here, magnetism is the comb, and the snake's dust is the smoke, sculpted by violence into something eerily beautiful. But the greatest puzzle is what lurks between the filaments. Most nebulae have uniform densities, but the snake's gaps are nearly empty, as if the dust was combed into starkly separated strands. Some theories suggest sonic waves, ripples from ancient supernova, might have vibrated through the cloud, pushing dust into magnetic valleys and leaving voids behind. Others propose an even wilder idea, that the snake isn't one nebula at all, but multiple clouds caught in a cosmic tug-of-war, their collisions stretching them into these bizarre forms. Whatever the truth, this nebula forces us to rewrite the rules. It's not just a dark cloud, it's a laboratory for physics we're only beginning to grasp, where magnetism and chaos dance in perfect, paradoxical harmony. And then there's the timing. The snake's filaments are transient. Within a few million years, they'll either collapse into stars or be torn apart by those nearby stellar giants. We're witnessing a fleeting moment, a snapshot of cosmic forces in exquisite balance. That rarity makes every observation precious. Telescopes like ALMA have detected faint glow from molecules trapped in the dust, hinting at chemistry we've never seen in such an environment. Could these magnetic prisons be incubators for complex organic compounds? The more we study the snake, the clearer it becomes. This isn't just a shadow in the sky. It's a challenge to everything we thought we knew about how the universe builds its structures and what might be hiding in the dark. Tucked away in Orion's sword, Lynn's dark nebula 1622 looms like a phantom against the constellation's glowing backdrop. Unlike the ragged edges of most dark clouds, this one presents an almost polished silhouette, a sharply defined stain on the cosmos that seems to absorb starlight with unnatural efficiency. Its darkness isn't just an absence, it's a statement so dense that even the brightest nearby stars fail to puncture its veil. That density raises eyebrows. Typically, dark nebulae are porous, their dust and gas loosely woven enough to let some light trickle through. But LDN 1622 defies the norm, packing its material so tightly it rivals the opacity of a closed curtain. The mystery deepens when you consider its structure. From Earth, it appears as a singular blotch, but zoom in with radio telescopes and the story fractures. Some observations suggest it's not one nebula at all. Instead, multiple clouds stacked along our line of sight, their combined shadows creating the illusion of a single monstrous void. Imagine holding two sheets of black paper slightly apart. From the right angle, they'd merge into one darker shape. That's the puzzle here. If it's multiple clouds, their near-perfect alignment challenges probability, as if the universe orchestrated a cosmic sleight of hand. Yet there's another camp of researchers who argue the opposite. They point to the nebula's shockingly uniform density, a trait rarely seen in overlapping clouds, which usually show patchy variations. This camp believes LDN 1622 is a single, unusually coherent structure, a supercloud, whose internal turbulence somehow settled into eerie equilibrium. Supporting this, infrared scans reveal subtle, swirling patterns in its depths, like fingerprints left by a single gravitational hand. The debate isn't just academic, it cuts to the heart of how we classify cosmic shadows. Are we seeing one entity or a celestial mirage? What's undeniable is the nebula's role as a stellar roadblock. Orion's sword is a hotspot for star formation, but behind LDN 1622, the stellar nursery goes quiet. It's as if the nebula erected a wall, shielding a pocket of space from the intense radiation needed to spark new stars. Some theorists suggest this isolation might preserve primordial gas unchanged since the galaxy's infancy, making it a goldmine for studying the raw ingredients of star birth. Others speculate that the cloud's extreme density could be crushing its own material into protostars so faint, our instruments haven't spotted them yet. Then there's the ghostly glow. In certain wavelengths, the nebula's edges emit a faint luminescence caused by cosmic rays exciting its molecules. This halo isn't just eerie, it's a clue. The light's polarization patterns hint at magnetic fields wrapping around the cloud like a net, potentially explaining its unnaturally tight structure. If confirmed, it would mean LDN 1622 isn't just hiding in Orion's shadow. It's being sculpted by forces we've barely begun to map. Every observation peels back another layer, but the core question remains: is this a cosmic coincidence or a lone titan of darkness? Until we know, it stands as a haunting reminder that even the blackest voids can hold the universe's sharpest secrets. The Pipe Nebula cuts a striking figure against the Milky Way's glow. A long, stem-like trail of darkness curving through Ophiuchus with such clarity it feels almost artificial. From Earth, its silhouette unmistakably resembles a smoker's pipe, complete with a rounded bowl and an elongated stem stretching across 40 light-years of space. Unlike the tangled chaos of most dark nebulae, this one presents an almost refined structure, as if the universe decided to sketch a celestial still life against the starry canvas. But behind its familiar shape lies a puzzle. For a nebula this large and dense, the pipe should be teeming with young stars, their birth ignited by collapsing gas. Yet scans reveal an unsettling quiet, as if this stretch of space hit the cosmic pause button. What makes this absence so perplexing is the nebula's composition. Its dust grains are rich in silicates and carbon compounds, the very materials that typically clump together to form protostars. Under normal circumstances, gravity should have already pulled these particles into dense cores, sparking new stellar fires. Instead, the pipe's interior remains cold and still, with only faint whispers of turbulence rippling through its filaments. Some astronomers suggest external forces might be at play. The nebula drifts near the edge of the Good Belt, a vast ring of bright stars and gas encircling our solar system. Radiation and shockwaves from this belt could be disrupting the pipe's collapse, like a gust of wind preventing sand from settling into dunes. Yet there's another layer to the mystery. The pipe isn't an isolated shadow. It's part of a sprawling network of dark nebulae collectively known as the Ophiuchus dust complex. Together, these clouds weave through space like ink blots on a galactic map, tracing the contours of an unseen interstellar scaffold. Infrared surveys reveal they're connected by tendrils of colder, thinner dust, a hidden web that channels material across hundreds of light years. The pipe might appear solitary to our eyes, but it's just one visible knot in this vast cosmic tapestry. And then there's the age factor. While most nebulae disperse within a few million years, the pipe's dust grains show signs of being unusually ancient, some possibly older than the Sun. Their survival suggests an environment of remarkable stability, sheltered from the supernova and stellar winds that typically erode such structures. This longevity could explain the lack of star formation without disruptive shocks to trigger collapse. The gas remains suspended in equilibrium like a cloud frozen mid-fall. But the most tantalizing clue lies in motion. Recent radio observations show the pipe's stem isn't static. It's slowly unraveling, its material streaming toward the nearby Rho Ophiuchi star-forming region. This outflow hints at a hidden relationship. Perhaps the pipe isn't dormant after all, but quietly feeding its brighter neighbor, supplying raw material for stars born elsewhere. If true, it transforms our understanding of the nebula from a cosmic dead zone into a vital artery in the galaxy's circulatory system. The pipe's darkness, then, isn't an end. It's a conduit shaping stellar destinies in ways we're only beginning to trace. The Pipe Nebula's striking silhouette hides a chemical riddle. Its stem and bowl aren't just visually distinct, they're made of fundamentally different stuff. While the bowl's dust grains shimmer with frozen carbon monoxide and complex hydrocarbons, the stem's composition skews heavier, laced with silicate minerals and metallic compounds usually forged in supernova explosions. This mismatch defies expectations. Nebulae typically form from homogeneous clouds, their chemistry uniform across vast stretches. But here, it's as if someone stitched two cosmic fabrics together, leaving astronomers to wonder, did these sections arise from separate events, or does some unseen process sort elements like a celestial sieve? One clue lies in their temperatures. The bowl's gases hover near 10 degrees above absolute zero, so cold that molecules move at a glacial pace, preserving delicate carbon chains. Meanwhile, the stem runs slightly warmer, its dust grains vibrating enough to shed fragile ices, leaving behind hardy silicates. This thermal divide suggests the stem might be closer to hidden heat sources, perhaps young stars buried in adjacent clouds, their radiation gently warming the nebula's spine. Yet infrared scans reveal no such stars close enough to explain the disparity. Alternative theories point to magnetic fields, which could funnel heavier particles into the stem while lighter molecules pool in the bowl's gravitational lows, a cosmic sorting mechanism we've never observed at this scale. Then there's the motion data. Radio telescopes tracking gas velocities show the stem drifting toward Rho Ophiuchi at a brisk 7 kilometers per second, twice the speed of the bowl's leisurely pace. This kinetic mismatch fuels the separate origins hypothesis. Some researchers propose the stem could be a rogue filament, captured by the bowl's gravity only recently, its metallic richness hinting at a violent birthplace near an ancient supernova. Others argue the entire nebula might be a collision site where two clouds with distinct histories slammed together, their chemistry forever marked by the encounter. But the most tantalizing evidence comes from stardust, literally. The stem contains an overabundance of presolar grains, microscopic minerals older than the sun, forged in the hearts of long-dead stars. These tiny time capsules are rare in most nebulae, yet here they cluster like buried treasure. Their presence suggests the stem might be a relic of the galaxy's wilder youth, a shard of interstellar material that escaped billions of years of cosmic recycling. The bowl, by contrast, shows a cleaner, more modern signature, its chemistry reflecting the smoother evolution of a quieter era. This duality transforms the pipe from a simple shadow into a cosmic palimpsest, its two sections whispering different chapters of galactic history. If the bowl is a quiet eddy in the Milky Way's flow, the stem might be a fossil of its turbulent past. Unraveling their shared story could rewrite how we understand dark nebulae, not just as passive curtains of dust, but as dynamic archives etching the universe's secrets in chemistry and light. Every observation deepens the intrigue, proving even the simplest shapes can harbor the most complex tales. Just 450 light-years from Earth, a stone's throw in cosmic terms, the Taurus molecular cloud drifts like a sprawling archipelago of shadow. This isn't some distant, monolithic nebula. It's a fractured maze of dark filaments and isolated clumps, each with its own story. So close that individual dust grains cast subtle shadows on background stars, Taurus offers a front-row seat to the messy, uneven process of star birth. But here's the puzzle. While parts of the cloud are bustling stellar nurseries, others linger in eerie stillness, their gas frozen in time. How can one nebula be so alive in places and so dormant in others? The answer begins with structure. Unlike the Pipe Nebula's smooth contours or Barnard's 68's perfect sphere, Taurus is a cosmic jigsaw puzzle. Its fragments range from dense cores massive enough to birth suns to wispy strands too thin to hold together. Some knots collapse under their own weight, igniting protostars, while neighboring pockets, just as dense, defy gravity's pull. Infrared telescopes reveal why turbulence. Gas swirls through the cloud at supersonic speeds, creating chaotic pockets where pressure battles gravity to a standstill. Picture a pot of boiling water. Some bubbles merge and burst, while others linger, trapped by unseen currents. Yet turbulence alone doesn't explain the stark divides. Take Barnard 213, a dark knot within Taurus where stars are noticeably absent. Its gas is cold, colder than expected, with molecules like carbon monoxide frozen into icy shells around dust grains. This interstellar frost acts like glue, stiffening the cloud and resisting collapse. Nearby, a region like L1500 glows with young stars, its chemistry dominated by warmer, more reactive compounds. The difference: exposure. L1500 sits closer to the Pleiades, whose brilliant stars bathe it in just enough heat to keep its gases fluid and primed for collapse. Barnard 213, meanwhile, hides in Taurus's shadow, its chemistry locked in deep freeze. But the real revelation came when astronomers mapped the cloud's magnetic fields. Filaments aligned like compass needles trace invisible lines of force, channeling material into some areas and starving others. In active zones, these fields funnel gas efficiently, piling it up until gravity takes over. In quiet zones, they act as barriers, propping up the cloud against collapse like cosmic scaffolding. It's a delicate balance, one that explains why stars don't form uniformly, even within the same nebula. And then there's timing. Some dormant regions may simply be late bloomers, their collapse delayed by 1,000,000 years or more. Others might never ignite at all, destined to dissipate as the galaxy's spiral arms tug them apart. Taurus, with its mix of bustling nurseries and silent voids, forces us to confront a humbling truth. Star formation isn't just about density and gravity. It's a dance of chemistry, magnetism, and sheer cosmic luck, a reminder that even in the darkest clouds, the universe keeps its most intimate rhythms just out of reach. Stretching like a charcoal smudge across the constellation Musca, the dark doodad earns its playful nickname from the way it seems to scribble itself against the Milky Way's glow. This isn't just another shadowy blot in the cosmos, it's a sleek, serpentine ribbon of dust and gas, over 30 light-years long but barely 3 wide, as if the universe took a fine-tipped pen and drew a single, deliberate line through the stars. Yet what makes it truly unusual isn't its shape, but the way it plays with light. Most dark nebulae swallow photons whole, but the doodad scatters just enough starlight to give its edges an eerie blue-gray sheen, like moonlit smoke curling through the night. This ghostly glow comes from an odd quirk of physics. While the nebula's core is dense enough to block visible light, its outermost layers are peppered with microscopic dust grains particles just the right size to catch and re-emit the faintest traces of radiation from nearby stars. The effect, called reflection nebulosity, is rare in dark nebulae, which typically absorb or obscure light entirely. It's as if the doodad can't decide whether to hide or reveal itself, caught between shadow and shimmer. But the real mystery lies in its spine. Running the length of the nebula is a near-perfect filament of even denser material, a backbone of sorts that glows faintly in submillimeter wavelengths. Some researchers believe this spine is a relic of the nebula's formation, a remnant of the shockwave from a long-dead supernova that compressed gas into this bizarre, thread-like shape. Others argue it's the work of magnetic fields, which could have combed the dust into alignment like iron filings around a magnet. Either way, the spine's precision defies the chaos of interstellar space, suggesting forces at work we've yet to fully understand. And then there's the silence. Despite its size and structure, the dark doodad shows almost no signs of star formation. No protostars, no heat signatures, just cold, quiet dust. This dormancy is puzzling, given that similar filaments in other nebulae often fracture into stellar nurseries. One theory points to its motion. The doodad is racing through space at an unusual angle relative to the galaxy's rotation, its velocity perhaps preventing gravitational collapse. Another idea involves its chemistry. Spectrographs reveal an overabundance of carbon chains, which might act like cosmic Velcro, keeping dust grains stuck together just enough to resist fragmentation. Yet the most captivating detail might be its impermanence. The doodad's delicate balance won't last. In a few million years, tidal forces from the galaxy's rotation will likely shred it into fragments, some collapsing into stars, others dispersing into the void. We're witnessing a fleeting masterpiece, a dark brushstroke across the cosmos that will vanish as suddenly as it appeared. For now, it remains a paradox, a nebula that's both dark and luminous, structured and ephemeral, a reminder that even the simplest shadows can hold the universe's most intricate secrets. Lupus 3 isn't your typical stellar nursery. Nestled 500 light-years away in the constellation Lupus, this dark nebula crackles with an energy that defies expectations. A chaotic ballet of collapsing gas and newborn stars unfolding at breakneck speed. While most nebulae take millions of years to gestate stars, Lupus 3 operates on a cosmic fast-forward, condensing protostars in what seems like the blink of an eye. But the real shock isn't just the pace, it's the gaps. Scattered through its dust like missing puzzle pieces, vast voids disrupt the nebula's structure as if something or someone reached in and scooped out handfuls of darkness. At its heart, Lupus 3 cradles some of the youngest stars ever observed, their feeble glow barely piercing the surrounding gloom. These aren't the dignified, slowly maturing sons of Orion's nurseries. They're cosmic toddlers, eruptive and unpredictable, flickering with violent outbursts as they greedily devour surrounding gas. Infrared telescopes reveal jets of material shooting from their poles at hundreds of kilometers per second, a sign of their frantic growth. Normally, this turbulence would slow star formation, but here it seems to accelerate it. The nebula's magnetic fields, unusually weak for such an active region, might be the culprit. Without their typical restraining influence, gravity runs wild, crumpling gas into stars before the usual checks and balances kick in, yet the gaps steal the spotlight. Unlike the irregular voids seen in other nebulae, Lupus 3's empty patches are strikingly round, some spanning multiple light-years. One theory blames the nebula's rowdy young stars. Their fierce radiation and stellar winds could be blowing bubbles in the dust like a child exhaling through chocolate milk. But there's a problem. The gap's edges are too sharp, their shapes too perfect for mere stellar breezes. Another idea suggests passing rogue planets' worlds ejected from nearby systems might be plowing through the nebula, clearing paths like ships through fog. The most tantalizing possibility, ancient supernova. Submillimeter scans detect faint ripples around some voids, hinting at shockwaves from long-dead stars that punched holes in the cloud eons ago. What makes Lupus 3 truly extraordinary is its snapshot of imbalance. In most nurseries, star formation self-regulates. Newborns eventually stir up enough chaos to halt further births. But here, the process runs unchecked, as if the nebula's internal brakes have failed. Some astronomers speculate this frenzy might be a glimpse of the early universe, when stars formed in reckless bursts, unfettered by the heavier elements that now slow things down. Others see it as evidence of an external trigger, perhaps a nearby cluster's gravity yanking the nebula like a sheet, shaking loose pockets of gas to collapse. One thing's certain, Lupus 3 refuses to follow the rules. It's a cosmic paradox where stillness and violence coexist, where gaps in the dark might hold clues to the brightest beginnings. Every observation peels back another layer, but the core question lingers. Is this nebula a relic of a wilder past or a preview of stellar chaos yet to come? Floating alone in the Cygnus constellation like a spilled drop of cosmic ink, The ink spot nebula stands out not just for its darkness but for its sheer independence. Unlike most dark nebulae, which cluster in star-forming regions or drift along spiral arms, this one sits in near total solitude, a lonely island of dust adrift in an ocean of void. Its isolation is so profound that astronomers initially mistook it for a flaw in their photographic plates, a smudge on the lens rather than a feature of deep space. But the ink spot is very real, and its near-perfect opacity makes it one of the darkest known objects in the galaxy. Light doesn't merely dim as it passes through, it vanishes entirely, swallowed by dust grains packed so tightly they create a blackness deeper than the space between stars. What makes this nebula's density so extraordinary is its defiance of the usual rules. Molecular clouds this thick typically collapse under their own weight, birthing stars or at least fragmenting into clumps. Yet the ink spot holds its form with eerie stability, its particles suspended as if frozen in time. Some researchers point to its peculiar chemistry. Spectrographs reveal an unusually high concentration of complex carbon molecules, which might act like microscopic Velcro, binding dust grains together just enough to resist gravity's pull. Others argue its isolation is key. With no nearby stars to bombard it with radiation or shockwaves, the nebula exists in a state of suspended animation, untroubled by the forces that usually stir cosmic clouds into action. But the most startling theory suggests the ink spot isn't a nebula at all, at least, not in the traditional sense. Its temperature profile matches models of pre-supernova shells, the dense shrouds of material expelled by massive stars in their death throes. If true, this patch of darkness could be the ghost of a stellar giant that vanished long ago, its outer layers collapsing inward to form this ultra-dense shroud. Supporting this, radio telescopes have detected faint whispers of ionized gas at the nebula's edges, a possible relic of the star's final outburst, the kicker. Simulations show the ink spot's current mass and structure could, in a few million years, collapse into a new generation of stars or even reignite as a supernova itself. Imagine a dark nebula that's not just a stellar grave but a future stellar cradle or bomb. Then there's the mystery of its shape. Most nebulae this dense are irregular, torn by internal turbulence. But the ink spot is almost perfectly spherical, a geometry so rare in dark clouds that it sparked debate about hidden forces at work. Some propose an ancient magnetic field, long since faded, might have sculpted it into this form. Others wonder if it's the aftermath of a collision, two clouds slamming together with such precision they merged into this unsettlingly smooth orb. Every observation deepens the intrigue, revealing a structure that shouldn't exist, in a place it shouldn't be, doing nothing when it should be doing something. For now, the ink spot just hangs there, a cosmic enigma wrapped in perfect blackness. Whether it's a relic of a dead star, a future supernova in waiting, or something else entirely, one thing's certain: it's proof that even the darkest corners of space can hold the brightest sparks of mystery. And as telescopes grow sharper, who knows what secrets will pry from its silent depths? Behind the iconic Horsehead Nebula's silhouette lies a darkness even more enigmatic, a vast shadow where the usual rules of cosmic evolution seem to break down. While the Horsehead itself steals attention with its striking profile, this neighboring void, officially part of the larger Orion B molecular cloud, holds mysteries that defy expectations. Most dark nebulae maintain relatively stable temperatures, chilling to near absolute zero as they block out starlight. But here, astronomers have detected wild, unpredictable fluctuations, pockets of gas swinging between extremes, some zones plunging colder than expected while others simmer unexpectedly warm. These variations aren't just odd, they challenge our fundamental models of how nebulae behave. What makes these temperature swings so baffling is their lack of obvious cause. In active star-forming regions, newborn stars heat their surroundings, creating thermal unevenness. Yet the shadow behind the Horsehead shows no such stellar activity. no hidden protostars, no energetic jets. Instead, the warmth seems to emerge from the nebula itself, as if its dust grains are generating heat through some unseen mechanism. One theory points to cosmic rays, high-energy particles from distant supernova slamming into the cloud's molecules and triggering subtle warming. Another suggests magnetic fields could be twisting the gas filaments, creating friction that releases energy. Then there's the darkest horse in this race, the possibility of exotic chemistry. The region harbors unusual concentrations of hydrogen cyanide and formaldehyde, molecules that can absorb and re-emit energy in unexpected ways. Could chemical reactions be cooking the nebula from within? The cold spots deepen the puzzle. Some areas dip below 10 degrees Kelvin colder than most interstellar space despite being nestled within a denser cloud that should retain heat. One explanation involves quantum physics. At these extreme lows, hydrogen molecules might enter a rare quantum state called ortho-para transition, releasing energy as they shift forms and effectively refrigerating their surroundings. It's as if the nebula has built-in air conditioning, with certain zones sucking heat from their neighbors. But the real shock came when researchers mapped these temperature variations against the nebula's structure. The hottest and coldest patches align in eerie geometric patterns, hexagons and spirals etched into the darkness, shapes that mirror fluid dynamics experiments more than interstellar clouds. Some scientists speculate this could hint at sound waves trapped within the nebula, vibrating at frequencies that organize the gas into thermal zones. Others see the ghostly hand of magnetic fields sculpting the chaos into order. What's certain is that this shadowy companion to the horse head isn't just passive darkness. It's a dynamic, almost living entity humming with energy exchanges we're only beginning to decode. Every new observation peels back another layer, revealing a nebula that doesn't just obscure light, it plays with it, bending the rules of physics in ways that keep astronomers tossing theories into the cosmic void. And as we stare deeper into its folds, one question lingers. If such ordinary-looking darkness can hide this much complexity, what other secrets might the universe's shadows hold? Rising from the cosmic dust like a monolith of shadow, the Cone Nebula's base is where gravity itself seems to hesitate. Towering over 7 light-years tall, this dense pillar in the constellation Monoceros should be a stellar factory, its sheer mass more than enough to trigger runaway star formation. Yet the core remains eerily still, as if the laws of physics have hit an invisible break. The reason? A delicate tug of war between forces where gravity's pull is matched step for step by outward pressure, creating a cosmic stalemate that's left astronomers both fascinated and baffled. Most molecular clouds collapse when their internal gas pressure can't resist gravity's crush. But the cone's base defies this expectation, its gases held aloft by an unseen hand. Infrared telescopes reveal the culprit. Turbulent supersonic winds, channeled by the nebula's funnel-like shape, roar through its depths at speeds exceeding 150,000 kilometers per hour. These winds don't just stir the cloud, they prop it up, like a blast of air keeping a beach ball suspended midair. Meanwhile, magnetic fields weave through the chaos, their lines acting like reinforcing rods in concrete, adding rigidity to the structure. The result is a bizarre equilibrium where material piles up but refuses to collapse, like a snowdrift that somehow never avalanches. But the real mystery lies deeper. Submillimeter scans show the base isn't uniform, it's riddled with knots, dense pockets that should be hotbeds of star birth. Yet these knots glow faintly, their cores too warm to collapse but too cool to ignite. One theory points to an external radiation source, nearby massive stars bombarding the knots with just enough energy to keep them simmering, like a pot left on low heat. Another idea involves exotic chemistry. The knots are rich in frozen carbon monoxide, whose molecules may act like miniature shock absorbers, dissipating gravitational energy as subtle vibrations rather than letting it build toward collapse. The most tantalizing clue comes from motion. Gas streams within the cone's base don't flow inward as models predict. They spiral sideways, wrapping around the pillar in helical patterns reminiscent of a barber's pole. This suggests angular momentum plays an unexpected role, with the nebula's rotation fighting gravity's pull. It's as if the entire structure is a cosmic centrifuge, flinging material outward even as gravity tries to draw it in. For now, the cone's base remains a paradox, a place where stars should blaze but don't, where darkness isn't just an absence of light but a defiance of expectation. Every observation peels back another layer, revealing a celestial balancing act so precise it could unravel with the slightest nudge, and when it does, the heavens might gain a new cluster of stars, or this enigmatic pillar might simply dissolve, its secrets lost to the void. Either way, it stands as a humbling reminder. Even in the cold grasp of gravity, the universe reserves the right to pause, ponder, and play by its own rules. Stretching across the Circinus constellation like a phantom arachnid, the Black Widow Nebula spins a cosmic web unlike any other. Its filaments, dark, intricate, and eerily symmetrical, radiate outward in patterns so precise they seem almost artificial. But this isn't the work of some celestial weaver. It's the aftermath of violence. At its heart lies a runaway star, a blazing behemoth hurling stellar winds at nearly 3,000 kilometers per second. These winds don't just sculpt the nebula, they electrify it, carving channels through the surrounding dust with the precision of a laser. The result, a structure so finely detailed that its faintest tendrils stretch over 15 light-years, each one a roadmap of the star's ferocious energy. What makes the Widow's Web truly bizarre is how it interacts with its environment. Normally, nebulae merge seamlessly with nearby gas clouds, their edges blurring into the interstellar medium. But here, the filaments don't blend, they repel. Observations from the Atacama Large Millimeter Array reveal ghostly halos around each strand, where magnetic fields and radiation pressure push against neighboring clouds like invisible force fields. This creates stark boundaries, as if the nebula has drawn territorial lines in the cosmos. Some researchers compare it to oil-resisting water, with the Widow's dust-laden filaments refusing to mix with the hydrogen-rich clouds around them. The secret might lie in chemistry. Spectroscopy shows the filaments are laced with polycyclic aromatic hydrocarbons, complex carbon molecules that act like microscopic armor, stiffening the dust against erosion. When the central star's winds slam into these structures, they don't scatter randomly. They channel along the hydrocarbon chains, reinforcing the web's shape instead of destroying it. It's a self-perpetuating cycle. The harder the winds blow, the more defined the web becomes. But the real showstopper is the Widow's legs' 8 primary filaments that curve backward, as if recoiling from their own creation. Doppler measurements reveal these aren't static structures. They're accelerating, their tips fleeing the central star at speeds that defy simple gravitational models. The leading theory, they're caught in a cosmic tug-of-war between the star's radiation and the gravitational pull of a nearby molecular cloud. This unseen duel stretches the filaments into their signature arched shapes, like ribbons fluttering in a hurricane. Yet the most chilling detail might be the silence. Despite the central star's fury, the Widow's Web shows almost no star formation, a stark contrast to most wind-sculpted nebulae, where shockwaves typically trigger stellar birth. Instead, the filaments seem to smother any potential protostars, their magnetic fields and turbulence creating conditions too chaotic for collapse. It's as if the nebula isn't just a spider's web, but a predator's trap, a structure designed to strangle new suns before they can ignite. As we unravel the Widow's mysteries, one thing becomes clear: this isn't just another dark nebula. It's a celestial battlefield where stellar winds, magnetism, and chemistry clash in a delicate dance of destruction and preservation. And with every new observation, we're forced to ask, is this the universe's way of weaving art from chaos, or are we witnessing something far more sinister? Looming over the heart of Scorpius like a sentinel of the void, the Dark Tower Nebula is a structure so immense it defies belief. Stretching nearly 50 light-years from base to tip, this monstrous pillar of gas and dust stands tall enough to dwarf entire star clusters, casting a shadow so deep it blots out the galactic core behind it. But what truly unnerves astronomers isn't its size, it's the silence. While most nebulae of this scale crackle with the infrared glow of hidden protostars, the tower's core emits nothing. No heat, no light, just an abyss so profound it's earned the nickname the Cosmic Graveyard, as if something inside is swallowing energy whole. Peering into this darkness reveals a paradox. The tower's outer layers bristle with activity. Stellar winds from nearby giants sculpt its ridges into eerie, wave-like patterns, while ultraviolet radiation ionizes its surface into faintly luminous tendrils. But step by step toward the core, the signals fade, as if the nebula's heart has been hollowed out. Submillimeter telescopes detect dense knots of material there, exactly where star formation should be rampant, yet these clumps remain frozen in time. Some researchers speculate that magnetic fields, twisted into cosmic knots, might be strangling the collapse before it can begin. Others point to the nebula's unique chemistry. Spectrographs reveal bizarrely high concentrations of molecular nitrogen, a gas that absorbs heat with unnatural efficiency, potentially acting like a cosmic refrigerant to keep the core in perpetual deep freeze. Then there's the spine. Running vertically through the tower is a filament so perfectly straight it seems artificial, a dark lightning bolt connecting the nebula's base to its crown. This spine doesn't just defy the chaotic turbulence of most nebulae, it pulses. Radio observations show rhythmic fluctuations in its density, as if some unseen force is vibrating the entire structure like a plucked string. One theory suggests a long-dead black hole might lurk at the nebula's base, its gravity sending shockwaves through the gas. Another proposes an ancient supernova shockwave, frozen in time as it rippled through the cloud. The nickname Cosmic Graveyard takes on grim weight when you consider the corpses. Nestled in the tower's lower reaches are the remnants of failed stars, brown dwarfs so cold they barely register on telescopes, and rogue planets cast adrift from their solar systems. These objects, too faint to warm their surroundings, only deepen the nebula's eerie reputation. It's as if the tower isn't just a place where stars refuse to form, but where celestial ambitions go to die. Yet even here, there's a whisper of defiance. Recent studies hint at a single, struggling protostar buried deep in the tower's midsection, a flicker of heat fighting against the darkness. Whether it will succeed or be snuffed out remains one of Scorpius' most haunting questions. For now, the Dark Tower stands as a monument to stillness, its secrets locked in ice and shadow, daring us to unravel how such a place could exist in a universe teeming with light. The Elephant's Trunk Nebula is famous for its sweeping silhouette, a towering column of dust that resembles a celestial proboscis reaching across space. But inside that iconic shape, something far stranger twists in the darkness. The trunk's core isn't just dense, it's structured with dust spiraling in precise, helical patterns that defy the chaos of typical nebulae. These aren't random swirls, they're cosmic fingerprints, left behind by magnetic fields so powerful they've sculpted chaos into near-perfect geometry. Peering into the trunk's shadowy heart reveals a labyrinth of braided filaments, each one a helix of dust grains aligned like iron filings around a magnet. Normally, turbulence would shred such delicate order, yet here the patterns persist. The secret, a magnetic field stronger than any observed in similar nebulae, weaving through the gas with enough force to corral particles into these eerie, spiraling tracks. Submillimeter telescopes have mapped these fields in stunning detail, lines of force so tightly wound they resemble the grooves of a cosmic screw. It's as if the nebula's core is threaded with invisible wires, guiding dust into formations that shouldn't survive the violence of interstellar space. What's even more surprising is how these helices interact with light. While the trunk's outer layers absorb or scatter starlight, the helical cores polarize it, twisting photons into spirals that match the dust's own curves. This isn't just a dark nebula, it's a cosmic prism, bending light in ways that reveal hidden magnetic architectures. Some filaments even glow faintly in polarized light, their dust grains acting like microscopic mirrors to reflect the unseen forces shaping them. Then there's the motion. Doppler studies show the helices aren't static, they're spinning, their dusty strands unraveling and reforming at speeds that suggest relentless magnetic tension. One theory posits that the trunk is caught in a feedback loop. As the helices rotate, they amplify the nebula's magnetic field, which in turn tightens the spirals further. It's a self-perpetuating machine, a celestial dynamo hiding in plain sight. Yet the ultimate mystery isn't how these structures exist, it's what they're hiding. Nestled between the helices are pockets of near-perfect vacuum, voids where even the dust seems to shy away. Some researchers speculate these gaps could be cradles for rogue planets, their gravity hoovering up surrounding material. Others wonder if they're evidence of dark matter's invisible hand, subtly warping the nebula's fabric. For now, the trunk's core keeps its secrets, its dark helices spinning silently, a reminder that even the universe's most familiar shapes can harbor its most extraordinary riddles. The Ripple Nebula doesn't just drift through the Lupus constellation, it shimmers with the ghostly echoes of a cosmic catastrophe. Unlike the jagged edges of most dark nebulae, this cloud undulates in smooth, wave-like patterns, as if someone dragged a finger through celestial dust. These ripples aren't random, they're textbook evidence of a shockwave, likely from a supernova that erupted millions of years ago, its blast rippling through the cloud like a stone tossed into a pond. But here's what's strange, astronomers can't find the source. No neutron star, no black hole remnant, just these eerie, frozen waves stretching across 40 light-years of darkness, a cosmic cold case waiting to be solved. Infrared telescopes reveal the ripples in astonishing detail. Each crest and trough aligns with variations in density, where the shockwave compressed gas into towering ridges or stretched it into thin valleys. Some sections glow faintly with molecular hydrogen, excited by the ancient impact, while others remain eerily dark, their dust grains unscathed. This patchwork suggests the shockwave wasn't uniform, it hit unevenly, like a hammer striking an anvil at an angle. Yet the real puzzle isn't the pattern, it's the energy. Calculations show the supernova would have needed to explode with twice the force of a typical stellar death to sculpt these distortions. That points to a progenitor star far more massive than any found in Lupus today. Did it vanish without a trace, or is its remnant hiding in plain sight, camouflaged by the nebula's own shadows? Then there's the silence. Normally, a shockwave this powerful would trigger star formation, squeezing gas until it collapses into protostars, yet the Ripple Nebula shows no such activity. Its gases are too turbulent, their motions too chaotic to settle into gravitational surrender. It's as if the supernova's blast left the cloud permanently agitated, like a stirred pot that never stops swirling. Some researchers speculate this turbulence might be the key to the missing remnant. If the dying star's core was ejected at high speed, a kick from asymmetric forces during the explosion, it could now be racing through interstellar space, invisible to our telescopes but still felt through the nebula's restless motions. But the most tantalizing clue comes from chemistry. The nebula's ripples are rich in silicon carbide, a compound typically forged in supernova furnaces. These microscopic grains, scattered like cosmic breadcrumbs, trace a path back to the blast's epicenter. Follow them, and they lead to a void near the nebula's eastern edge, a region oddly devoid of dust. Could this be the exit wound where the shockwave burst free, leaving the nebula's ripples as its only signature? For now, the Ripple Nebula stands as a celestial palimpsest, its waves a fading record of violence long past. Every new observation peels back another layer, but the central mystery endures. Some of the universe's loudest explosions leave behind the quietest clues, written in dust and waiting for us to decode their whispers. Deep in the constellation Cepheus, the silent nebula floats like a cosmic mute button, a dark cloud so profoundly hushed it baffles every expectation. Radio telescopes, which normally pick up the faint whispers of molecular gases in nebulae, strain to detect even static from this void. Most clouds of similar size and density hum with radio emissions, their molecules vibrating as they collide. But here, the usual cosmic soundtrack cuts out, replaced by a silence so absolute it's as if the nebula has been draped in an interstellar noise-canceling blanket. This quiet isn't just unusual, it's theoretically jarring. The silent nebula's mass suggests it should be brimming with hydrogen molecules, the raw fuel of star birth, which typically emit telltale radio waves as they spin and vibrate. Yet scans reveal only the faintest traces, as though something has siphoned away their energy or locked them in a state of unnatural stillness. Some researchers point to the nebula's bizarrely low kinetic temperature, barely a hair above absolute zero. At such extremes, hydrogen molecules enter a quantum state called parahydrogen, where their spins align in ways that suppress radio emissions. It's a phenomenon seen in lab settings, but never before in a nebula of this scale. Then there's the dust. Unlike the jagged, porous grains found in most dark nebulae, the silent nebula's particles are smooth and spherical like microscopic marbles. These shapes, revealed by polarized light studies, scatter radiation with eerie efficiency, redirecting energy that would normally excite gas molecules into detectable signals. Imagine shouting into a room lined with velvet. The sound doesn't echo, it just vanishes. That's the effect here, only with starlight and radio waves instead of sound. But the real enigma is movement, or the lack of it. Doppler measurements show the nebula's gases drifting at a glacial pace, their turbulence dampened to a degree that defies the chaotic nature of interstellar clouds. One theory suggests an ancient magnetic field, long since faded, might have once acted like a cosmic brake, slowing the gas to this near standstill. Others speculate the nebula could be a failed filament, a strand of the cosmic web that never fully connected to a denser structure, leaving it suspended in isolation. The most haunting possibility, this silence isn't permanent. Submillimeter telescopes have detected faint, rhythmic pulsations in the nebula's core, waves of pressure so subtle they'd be missed without painstaking analysis. Some astronomers interpret these as the first stirrings of collapse, the nebula beginning to awaken from its slumber. If true, the silent nebula might not be silent forever. One day, its molecules could roar to life, igniting stars that will shatter the quiet with their birth cries. Until then, it remains a cosmic paradox, a dark cloud that refuses to speak, guarding its secrets in whispers too faint for even the universe to hear. Twisting through the constellation aura like a cosmic puzzle, the Maze Nebula earns its name with unsettling precision. Its filaments don't just meander, they branch, fork, and double back in patterns so intricate they resemble the blueprint of an ancient, forgotten labyrinth. Most dark nebulae sprawl in chaotic tangles, but here, the dust lanes align with near-geometric discipline, as if obeying some hidden design. Yet the real mystery lies in the dead ends. Scattered throughout the structure are cul-de-sacs of absolute darkness, tunnels of dust that lead nowhere, their abrupt terminations defying the usual flow of interstellar material. These aren't random gaps, they're deliberate-seeming closures like corridors walled off by an unseen hand. What makes these dead ends so perplexing is their resistance to erosion. The maze floats near a cluster of scorching young stars whose radiation should be shredding the nebula's delicate lanes. Yet the walls of these dust corridors stand unnervingly intact, their edges sharp as if freshly carved. Infrared observations reveal why. The nebula's dust grains are coated in a veneer of carbon-rich molecules, a sort of cosmic shellac that reflects and scatters radiation instead of absorbing it. It's as if the maze has built its own armor, weathering stellar winds that would have obliterated lesser clouds. But the strangest feature might be the silence at its center. While most labyrinthine nebulae hum with the radio signatures of collapsing gas, the maze's heart emits nothing, no whispers of protostars, no telltale heat spikes. Instead, the core is a study in stillness, its gases locked in a state of suspended animation. Some researchers speculate this could be due to the nebula's unique magnetic fields, which crisscross its lanes like invisible rail tracks, channeling turbulence outward and leaving the center eerily calm. Others point to the dead ends themselves, suggesting they act as pressure valves, bleeding off energy that would otherwise trigger star formation. Then there's the motion. Doppler mapping shows the maze isn't static. Its filaments writhe slowly like snakes in zero gravity. Yet this movement follows no discernible pattern. Some lanes inch forward while others twist backward, as if the nebula is solving its own riddle in real time. The leading theory involves dark matter. Simulations suggest a clump of invisible mass might be drifting through the maze, its gravity warping the dust lanes like an unseen finger trailing through smoke. If true, it would mean this labyrinth isn't just a structure, it's a record of forces we can't see, a shadowy interaction playing out over millennia. For now, the maze keeps its secrets, its dead ends and silent core challenging every assumption about how dark nebulae evolve. Whether it's a cosmic accident or a masterpiece of physics we've yet to decode, one thing's certain: some puzzles aren't meant to be solved, only explored, one winding corridor at a time. Slithering through the constellation Vela like a ghostly scar, the phantom streak defies every rule of celestial permanence. Most dark nebulae remain unchanged over human lifetimes, their shadows cast across the same stars for millennia. But this wispy filament, barely 3 light-years wide and nearly invisible to most telescopes, flickers in and out of view over mere decades, as if the universe itself can't decide whether it should exist. When first documented in the 1950s, it appeared as a crisp, dark lane against the Milky Way's glow. By the 1980s, it had faded to a faint smudge. Then, in 2012, it reappeared with startling clarity, only to vanish again by 2020. This cosmic vanishing act has astronomers questioning whether they're observing a nebula at all, or something far stranger. The leading theory suggests the streak isn't a traditional dust cloud, but a light echo frozen in interstellar space. Imagine a supernova eruption centuries ago, its flash illuminating a pre-existing dust filament for a brief moment. The light would have traveled onward, leaving the filament dark until years later. A second burst of radiation from the same star's shockwave could reheat the dust, making it glow faintly before cooling back into obscurity. It's a celestial glitch, a replay of ancient light on a cosmic delay. Supporting this, radio telescopes have detected traces of iron-60, an isotope typically forged in supernova, lacing the streak's periphery like shrapnel from a stellar explosion. Yet even this explanation falters under scrutiny. The flickering occurs too rapidly. Supernova light echoes usually play out over centuries, not decades. Some researchers propose an even wilder idea, that the streak is a dust tsunami, a wall of particles being shoved forward by an invisible force, the culprit. A runaway neutron star, invisible to current telescopes, might be plowing through the interstellar medium at relativistic speeds, its bow shock compressing dust into temporary visibility before the particles disperse again. If true, the streak isn't a static structure, it's a wake, a fleeting ripple in the fabric of space-time. Then there's the polarization puzzle. When visible, the streak's light isn't just dim, it's twisted. Its electromagnetic waves aligned in spiral patterns that suggest powerful magnetic fields. Normally, such fields would stabilize a nebula, preventing the rapid changes the streak exhibits, unless the fields themselves are fluctuating. Recent studies point to a nearby gamma-ray burst remnant as the possible puppeteer. its decaying magnetic influence alternately squeezing and releasing the dust like an interstellar accordion. But the most haunting possibility is that the phantom streak doesn't belong to our galaxy at all. Its motion suggests an extragalactic origin, perhaps a shredded dwarf galaxy's debris strewn across our line of sight. In this scenario, the flickering could be caused by microlensing, as stars in the Milky Way's foreground pass between us and the distant dust, magnifying it unpredictably. That would make the streak less a nebula and more a cosmic illusion, a trick of perspective playing out over generations. For now, the phantom streak remains exactly what its name promises, an enigma that slips through our fingers with every observation. Whether it's a dying star's echo, a neutron star's footprint, or an entire galaxy's ghost, one thing is clear. Some shadows in the universe don't just obscure light, they dance with it. And with every flicker, they remind us how much we still have left to learn about the dark. Next to the Veil Nebula's famed gossamer tendrils, a supernova remnant so luminous it's visible through backyard telescopes, lies a shadowy twin few have noticed. The Veil's dark sister, an unnamed filament of dust in Cygnus, mirrors the Veil's sinuous shape almost exactly, but with a chilling twist. Where the Veil glows with ionized gas, this dark counterpart swallows light whole, its dust lanes coiled like a photographic negative of the explosion's aftermath. At first glance, it seems like mere camouflage, a chance alignment of foreground dust. But spectral analysis reveals something far stranger. The dark sister's particles bear the chemical fingerprints of a supernova, rich in silicon and iron isotopes, yet they're tangled in a structure too cold and dense to belong to the same cataclysm. It's as if two stellar deaths, one brilliant, one invisible, left identical scars across the cosmos. The puzzle deepens when you compare their timelines. The Veil's light echoes confirm its origin, a star that exploded roughly 8,000 years ago, its shockwave still expanding. Yet the dark sister's dust shows no such motion. Its grains drift with the sluggish pace of an older, weightier cloud, as if they've lingered for millennia before the Veil's birth. How could two structures with matching chemistry and geometry emerge from unrelated events? One radical theory suggests the dark sister isn't a remnant at all, but a pre-existing dust filament that recorded the Veil's explosion like cosmic film. When the supernova's shockwave plowed through it, the blast's heat might have forged new isotopes into the dust surface without dispersing the original structure, leaving a fossilized echo of the violence. Supporting this, ALMA telescope data reveals minuscule variations in the dark sister's magnetic fields, ripples that align precisely with the Veil's expansion pattern, as if the dust's invisible scaffolding was subtly rearranged by the blast. But there's a flaw. Supernova shocks typically shred dust clouds, not preserve them, unless the filament was already magnetically fortified, its particles locked into place by forces we've yet to measure. This would make the dark sister a cosmic anomaly, a structure sturdy enough to withstand a stellar apocalypse, yet fragile enough to bear its indelible mark. The most haunting possibility, the Veil and its shadow might be glimpses of the same event separated by time. Some models propose that supernova can trigger secondary collapses in nearby clouds, compressing them into dense, dark mirrors of the original remnant. If true, the dark sister could be the Veil's successor, a second act written in dust, waiting for its turn to ignite. Until then, it hangs in silence, a shadow where there should be light, a question where we expected certainty. And in that asymmetry, it reminds us, even the universe's most radiant explosions cast their darkest echoes. Drifting through the Hercules constellation like a relic from another age, the fossil nebula is a cosmic time capsule wrapped in darkness. Isolated from the galaxy's bustling star-forming regions, this ancient cloud harbors dust grains unlike any other's crystalline structures so pristine they're usually found only in the sheltered disks of newborn planetary systems. How such delicate order survived billions of years in the interstellar wilds is a puzzle that rewrites our understanding of cosmic material. These aren't the ragged, porous particles typical of dark nebulae. Under electron microscopes, they reveal geometric perfection, hexagonal patterns of olivine and pyroxene, minerals that should have been shattered eons ago by radiation and collisions. It's as if someone froze a protoplanetary disk in time and set it adrift among the stars. The key to their survival lies in the nebula's extreme isolation. Nestled in a quiet corner of the galaxy, far from supernova or turbulent stellar winds, the fossil nebula has avoided the violence that grinds most interstellar dust into amorphous blobs. But there's more. Spectral analysis reveals these crystals are coated in a thin veneer of carbon, a protective shell that acted like cosmic armor, deflecting radiation and preserving their atomic lattices. Imagine a snowflake surviving a journey through a sandblaster by wearing an invisible suit of diamond. That's the level of improbability at play here. Yet the real mystery isn't just their preservation, it's their origin. These crystals require specific conditions to form, temperatures above 700 degrees Celsius and pressures found only near young stars or deep inside planetary bodies. One theory suggests the nebula might be the shattered remains of a giant planetesimal, torn apart by gravitational forces and scattered into space. Others propose they're interstellar travelers, forged in the accretion disks of long-dead stars and ejected into the void only to be captured by this quiet cloud. Supporting this, isotopic ratios in the grains match those found in certain meteorites, hinting at a shared history with the building blocks of our own solar system. The most tantalizing clue, though, is motion. Unlike most nebulae where dust drifts in chaotic swirls, the fossil's grains move in eerie synchrony, as if guided by an unseen current. Radio telescopes have detected weak but coherent magnetic fields threading the cloud, their lines of force aligning the crystals like compass needles. This suggests the nebula might be a cosmic, still life, frozen not just in composition but in motion, a snapshot of forces that paused mid-action. What lessons does this ancient cloud hold? For astronomers, it's a Rosetta Stone for deciphering how planetary systems begin. These crystals are the raw ingredients of Earth-like worlds, preserved here in their original state. For the rest of us, it's a reminder that the universe keeps its secrets in the unlikeliest places, not just in the glare of stars, but in the quiet dark between them where time itself seems to hesitate. The hollow nebula looms in Scorpius like a cosmic enigma, a perfect ring of darkness encircling an empty center, as if someone cut a hole in the fabric of space itself. Unlike typical dark nebulae where voids form from stellar winds or radiation, this one's central gap defies explanation. No nearby stars blast energetic enough winds to carve such a precise, gaping chasm. Yet there it is, a donut of dust 7 light-years across, its edges unnervingly smooth, its core a perfect sphere of nothingness. Telescopes can't detect even trace gases lingering in that void, just absolute emptiness, a pocket of the universe that seems to have been evacuated by unseen hands. The strangest part, gravity should have collapsed that hole long ago. Nebulae this dense usually crumple inward, filling gaps as material spirals toward the center. But the hollow structure holds, its edges sharp as if propped up by some invisible scaffold. One theory points to dark matter, an unseen mass lurking at the nebula's core, its gravitational pull counterintuitively keeping the center clear by slingshotting dust outward like a cosmic sprinkler. Others suggest a rogue black hole might have punched through long ago, its passage stirring the nebula into this improbable shape before vanishing into the void. Supporting this, infrared surveys show faint heat signatures along the inner rim, as if something massive once orbited there, churning the dust into this eerie symmetry. Then there's the motion. Doppler scans reveal the nebula's outer layers rotating at different speeds, faster near the void, slower toward the edges, a pattern that mirrors galaxies circling supermassive black holes. But no black hole sits at the hollow's heart, unless it's hiding, Some astronomers speculate a rare, ultralight black hole could be the culprit, one so small it eludes current detection but massive enough to sculpt the gas around it. If true, this nebula might be the universe's cleverest game of hide and seek, with gravity's fingerprints everywhere but the suspect nowhere to be found. But the most tantalizing clue lies in chemistry. The hollow's innermost dust lanes are laced with rare isotopes of titanium and nickel metals typically forged in supernova. That suggests a cataclysmic explosion might have birthed this structure, its shockwave expanding outward in a perfect sphere, sweeping up material into the ring we see today. Yet there's no remnant of such an explosion at the center, no neutron star or pulsar to mark the star's grave. Just the hollow remains of a mystery, a cosmic crater with no impactor, a shadow where the light should be. For now, the hollow nebula keeps its secrets, a silent challenge to our understanding of how emptiness takes shape. Whether it's the work of dark matter, a vanished black hole, or a stellar death that left no corpse, one thing's certain: this isn't just another dark nebula. It's a celestial question mark, reminding us that even the emptiest corners of space can hold the universe's most stubborn riddles. Tucked away in Ophiuchus, the Mirror Nebula defies logic with its uncanny symmetry, a dark cloud that seems to duplicate its own structure like a cosmic inkblot test. Unlike the chaotic tangle of most nebulae, this one folds its dust lanes into near-perfect mirrored halves, as if an invisible pane of glass splits it down the center. Even stranger, the reflection isn't static. Infrared scans reveal subfilaments on one side shifting in real time, only for identical adjustments to appear moments later on the opposite flank, like a shadow mimicking its caster with zero delay. It's as if the nebula isn't just symmetrical but actively copying itself. The leading theory involves a gravitational anomaly, a dense, unseen object, perhaps a rogue black hole or neutron star might lurk between the mirrored halves, warping spacetime so severely that light and dust trajectories bend into this eerie duplication. Picture a stone dropped in a pond. The ripples symmetrically expand outward. Here, the stone is invisible, but its impact is written in the nebula's dust. Yet there's a flaw in this elegant idea. Spectroscopy detects no lensing effects or radiation from a central mass. If something's there, it's not just dark, it's utterly silent. Then there's the chemistry. Both sides of the nebula share identical molecular fingerprints, down to rare isotopes like aluminum-26, typically found in supernova debris. This suggests the mirroring isn't coincidental but intrinsic, a single cloud split and frozen mid-motion. Some researchers propose a violent stellar encounter tore the nebula in two, with magnetic fields freezing the halves in this mirrored pose. Others point to the nebula's location. It drifts along a cold spot in the interstellar medium, where temperatures are so uniform they might have preserved the symmetry of its birth. The most haunting detail comes from motion studies. ALMA telescope data shows the nebula's eastern side collapsing inward, while the western side simultaneously expands, as if playing a cosmic game of red light, green light. This anti-correlated motion defies fluid dynamics. Normally, turbulence would scramble such precision, unless the entire structure is resonating, vibrating like a struck tuning fork whose oscillations govern the dust's behavior. If true, the Mirror Nebula isn't just reflecting itself. It's singing in a key we can't yet hear, its symmetry conducting an orchestra of invisible forces. For now, this celestial doppelganger keeps its secrets, whether it's the work of hidden gravity, magnetic preservation, or some unknown physics. One thing's clear: in a universe built on chaos, the Mirror Nebula is a rebel's manifesto, a defiant whisper that symmetry can thrive even in the dark. The Vortex Nebula spins through the constellation Centaurus like a cosmic whirlpool, its dust and gas churning in patterns that defy every expectation. Dark nebulae are supposed to be static, cold, quiet, and chaotic. But here, the particles move in eerie unison, tracing spiral arms that mirror the grand design of a galaxy. It's as if someone took the Milky Way's graceful curves and shrank them into a shadowy maelstrom just 15 light-years wide. This isn't just unusual, it's unprecedented. Spiral structures require precise balances of rotation and gravity, forces we've only ever seen sculpt stars and galaxies, never the inky depths of a starless cloud. What's propelling this motion? The answer might lie in the nebula's hidden heart. Submillimeter telescopes have detected a subtle gravitational tug at the vortex's core, something massive enough to stir the gas into these swirling patterns, yet invisible in every wavelength we've searched. One theory suggests a failed star, a brown dwarf too faint to glow but hefty enough to pull the nebula into this eerie dance. Others propose a more exotic culprit. Primordial black holes, ancient relics from the universe's birth, could be lurking in the darkness, their gravity spinning the dust like a celestial mixer. But the real shock is the speed. The vortex's outer arms whip around at nearly 12 kilometers per second, faster than any known molecular cloud should move. Normally, turbulence or magnetic fields would shred such delicate spirals, yet here they hold their shape with unnatural precision. Radio observations reveal why. The nebula's particles are coated in magnetite, an iron-rich mineral that aligns them like compass needles along invisible field lines. These magnetic threads act like cosmic guide wires, channeling the chaos into orderly rotation. It's a phenomenon usually seen in accretion disks around black holes, not floating freely in the void. And then there's the silence. Despite all this motion, the vortex shows no signs of star formation. No protostars flicker in its arms, no heat signatures betray collapsing cores. This dormancy is its greatest paradox. Spiral density waves should compress gas, triggering stellar birth. Yet the vortex resists, its particles' content to swirl indefinitely, as if caught in a cosmic eddy where time itself slows down. Some researchers speculate its magnetic fields are too strong, propping up the gas against collapse. Others wonder if we're witnessing a snapshot, a fleeting moment before the spiral's arms finally fracture into clusters of newborn suns. The most haunting possibility, we're seeing a dark mirror of the early universe. Simulations suggest nebulae like this could have seeded the first galaxies, their swirling motions laying the groundwork for grander spirals to come. If true, the vortex isn't just an anomaly, it's a relic, a whisper from an era when darkness ruled, and the universe was still learning how to spin its brightest tales. The Echo Nebula lingers in Perseus like a cosmic recorder, playing back starlight with a delay that defies physics. When nearby stars flicker, dimming during solar flares or brightening with magnetic storms, this dark cloud doesn't just absorb their light. It replays it. Hours or even days later, faint echoes of those stellar fluctuations ripple through the nebula's dust lanes, as if the void itself has a memory. This isn't just reflection or scattering, it's a phenomenon with no clear precedent, suggesting the nebula bends light in ways our models can't yet explain. At first glance, the echo seems ordinary, a patch of interstellar dust about 50 light-years wide, dense enough to obscure the stars behind it. But radio telescopes picking up its whispers noticed something bizarre. The nebula's thermal emissions weren't just random noise. They pulsed in near-perfect sync with variable stars light-years away, but offset by precise time lag. It was as if the cloud had recorded those stars' activities and was playing them back on a cosmic delay. The most striking example came from the star GK Persei, a nova known for violent outbursts. When it erupted in 2007, X-ray telescopes captured the initial flare. Then, 19 hours later, the Echo Nebula's far side repeated the signal, down to the exact energy signature. No known process should allow dust to store and re-emit radiation with such fidelity. The leading theory involves an invisible lattice of ultra-dense plasma filaments threading the nebula. These hypothetical structures, predicted by some quantum gravity models but never observed, could act like cosmic fiber optics, trapping light in looping paths before releasing it slowly. Imagine shining a flashlight into a maze of mirrors. The beam bounces for hours before finally escaping. That's what might be happening here, only the mirrors are warped spacetime itself, twisted by the nebula's gravitational field into temporary light traps. Supporting this, submillimeter scans show the echo's dust grains are arranged in eerie alignment, their magnetic orientations unnaturally uniform, a sign something might be organizing them from within. Yet even this radical idea can't fully explain the echo's precision. The delays aren't random, they follow a logarithmic scale, like notes on a musical scale. A star's flicker might repeat after 8 hours, then 16, then 32, a pattern suggesting resonance, as if the nebula is tuned to certain cosmic frequencies. Some astrophysicists speculate this could point to acoustic spacetime, a fringe concept where gravitational waves vibrate the vacuum of space itself, creating standing waves that temporarily hold light before releasing it in sync. Others wonder if we're seeing evidence of higher dimensions, the nebula's dust bending light through unseen folds in reality, the most haunting possibility. The echo isn't unique. Revisiting old data, astronomers have spotted similar delayed signals from at least 3 other dark nebulae, all overlooked until now. If these clouds are indeed recording and replaying starlight, they might form a hidden network of cosmic archives, silent witnesses to stellar events we've long since missed. Every flicker, every flare, every stellar heartbeat might be stored in their depths, waiting for us to learn how to listen. Until then, the Echo Nebula lingers, a shadow that doesn't just obscure light but remembers it. The Ghost Nebula drifts through Cassiopeia like a celestial spectre, its wispy tendrils so faint they vanish when stared at directly, a cloud that shouldn't glow at all, yet flickers with eerie, inconsistent light. This isn't just another dark nebula, it's a cosmic anomaly, a structure astronomers have dubbed a zombie nebula for its uncanny ability to reanimate long after its star-forming energy should have faded. Most dark clouds shine only by the light they obscure, their silhouettes etched against brighter backgrounds. But the Ghost Nebula emits its own faint, ghostly luminescence, pulsing irregularly as if something unseen is breathing life into its dust. The key to this mystery lies in its chaotic past. Spectrographic analysis reveals the nebula's gases are laced with ionized particles, atoms stripped of electrons, a state typically caused by intense radiation from nearby stars. Yet the ghost floats in isolation, far from any obvious energy source. That is, until astronomers traced its trajectory backward through time. Millennia ago, a runaway star cluster, the Blue Rogue Assembly, barreled through this region of space at breakneck speed. These young, scorching stars didn't linger, but their passage might have been enough to electrify the nebula's dormant gases, like a match struck briefly in a dark room. The ghost's current flickering could be the fading afterglow of that encounter, a delayed reaction as its molecules slowly release the energy injected into them. But here's where the story twists. The nebula's emissions don't match the neat decay patterns of a one-time energy dump. Instead, they spike unpredictably, flaring in patches as if the cloud is being zapped by invisible cosmic defibrillators. Some researchers point to magnetized filaments woven through the nebula, invisible threads that might store and sporadically release energy like frayed power lines. Others propose a darker explanation. The Blue Rogue's visit left behind more than radiation. A few of its stars could have shed microquasars, tiny, hyperactive black holes that now skulk through the ghost's depths, their occasional feeding frenzies igniting the nebula's gases from within. The most haunting detail, though, is the ghost structure. Unlike most nebulae which fray at the edges, this one retains jagged, sharp boundaries as if sealed in an invisible force field. Radio telescopes have detected faint, coherent magnetic fields wrapping the cloud like a shell, a phenomenon usually seen around supernova remnants, not dormant dust clouds. This suggests the nebula might be a celestial matryoshka doll, its outer layers shielding a turbulent interior we can't yet see. For now, the Ghost Nebula lingers in Cassiopeia, a shadow that refuses to fade, flickering with borrowed light and half-told secrets. Whether it's the aftershock of a stellar drive-by or the hiding place of something far stranger, one thing's certain. In the cosmic graveyard of dark nebulae, this one hasn't finished telling its story. And as we listen to its whispers, we're reminded that even in the quietest corners of space, the past never truly dies, it just waits for the right moment to rise again. From the perfect symmetry of the Mirror Nebula to the haunting echoes of starlight trapped within the Echo Nebula, we've journeyed through 25 cosmic shadows that refuse to play by the universe's rules. These aren't just voids in space, they're laboratories of the bizarre, where magnetic fields sculpt dust into impossible shapes, where darkness pulses with memories of ancient explosions, and where entire nebulae flicker like candles in the cosmic wind. Each one challenges the textbook definition of what a nebula should be, proving that even the blackest corners of the cosmos hum with hidden physics we've barely begun to decipher. Take the hollow nebula's gaping void, defying gravity's pull for reasons we can't yet explain, or the Vortex Nebula spinning like a galaxy in miniature without a single star to anchor it. Consider the Ghost Nebula, a cosmic revenant flickering with borrowed light, or the Silent Nebula, where radio waves go to die in eerie, unexplainable quiet. These structures aren't passive curtains of dust, they're dynamic puzzles rewriting the rules of star formation, chemistry, and even time itself. And perhaps that's the most thrilling revelation: darkness isn't empty. It's a canvas for the universe's strangest artistry, where filaments braid into perfect helices, where dust grains align like soldiers under magnetic commands, and where echoes of the past replay with impossible precision. Every unanswered question, like why the Pipe Nebula's bowl and stem have different origins, or what force carved the Ripple Nebula's frozen waves, is a reminder that space still holds cards it hasn't shown us. So which of these cosmic enigmas lingers in your mind? Is it Barnard 68's unnerving symmetry, the Black Widow's predatory webs, or the fossil nebula's ancient crystals preserved like cosmic amber? Drop your favorite in the comments, because the best part of these mysteries is that they're not just for astronomers to solve. They're for all of us to wonder at, to debate, and to dream about as we stare up at the night sky, knowing that behind every shadow, the universe is spinning stories we've only just begun to read.